Okay, we go back to something serious. Okay, so I already tell you how about the accuracy in recovering a file, right? So 100% means, first of all, when you find that you delete the wrong file, you want to keep it, you want to recover it, the first thing is pull the pop-up. To avoid any circumstances that you have a chance of accidentally recycle or delete blocks. Then what? Then depend on the file size, right? Now, some of the file structure, I mean, it's not about data structure, right? It's file structure. Let's say the zip file. Okay, the zip file itself has checksum. What is checksum? Checksum means you reduce your whole bunch of things into 16 bytes, let's say. And 16 bytes kind of uniquely representing your file. We call it checksum. Okay? Usually, some of the file has checksum, zip file has checksum, I remember. So if zip file has checksum, that means DOCX, PPTX, Excel, all kind of things have checksum. You know that DOCX is zip file? Huh? No one knows? No, it is a zip file. No one knows it's a zip file. You guys are not geeky enough. Okay. Let me show you. So this is all my PowerPoint. Okay, of course I need to copy one as an experiment. Okay, experiment of PPTX. Okay. First, file it. Is it Microsoft PowerPoint? There's no way. I don't believe it. Rename it into a.zip. Yeah? Oh no, sorry. I have the wrong file name there. A.zip. Still think that it is PowerPoint? I don't believe it. Now I extract this. I have this directory, I have this directory, I have this directory. Yeah, they are all XMLs. Okay, they are all XMLs. So zip file is a DOCX zip file, Excel, PowerPoint, or a zip. Okay. So if that's the case, that means that if I want to recover this kind of file, my chance is quite high because I can first, doing a brute force search. Okay. I know that my DOC file span across 100 customers. But I don't know whether it is a sequentially allocated. Don't worry. Just pull the 100 continuous cluster and try once. If yes, good, I recover my file. If no, then it will know that this is not a correct file because the checksum itself is wrong. Okay? Usually the checksum is in the first cluster. Okay? Then you can do some brute force. Yeah. You have let's say 100 cluster in a disk, okay? And then you try to assemble another file randomly, or I don't know what is the way, okay? Maybe use recursion to do it, okay? To recover 10 blocks things and try to check the checksum and do it again and again, okay? Depends on how important your file is, okay? If this file is very important, let's say I spent 1 year to try to find it out, it's still worth it. Okay, so this is what I say that if you have a checksum, then you can use the file size as the handle to know how many blocks are needed and do a brute force recovery, which really works. Okay, so this is a FAT32 file system. This is the conclusion. This is a nice one, right? Because every little information, every little operation we can all understand. Very easy to understand, and we all know the operations. And although there are something like the file deletion, okay, I put a question mark here. So we don't know whether it's successful or not, right? I mean, you really mark it as deleted, but whether it's really deleted depends on later whether that free cluster, when you free it, is being recycled or not. Okay, and it's appear everywhere. You already know it. So in a later part of this PowerPoint, I usually keep it in here because I want to share with you, if you're interested, to understand other kind of allocation method. So we have something called index no allocation method. You can read it. Okay, while you're reading it, you will find something horrible like this. Okay, a big tree of allocation. This uses a tree as an allocation. We have other kind of allocation, like some using B tree. Okay, some are using other kind of data structure. Okay, in order to allocate a file. Okay, so I guess that's it about this PowerPoint. I will switch to the next topic. Okay, now this next topic is very important. How important it is. After you learn this part, you will understand what exactly is segmentation fault. What exactly is. How to use it efficiently. How to effectively have a segmentation fault. And you know why. Usually people, after taking this part, they will have one comment. Why don't you say it early? Why don't we take OS course before any programming course? But just because while you're doing a junior programming course, when people tell you that, oh, you see a segmentation course, they don't try to give you an understanding. They will tell you that you do something wrong, fix it. But what exactly is that? Right? What exactly is the thing that you do it wrong? Here I will explain every possible cases that you will generate segmentation fault. It's every. Okay? No any one missing case. Okay? So this is about user space memory. User space memory. So whenever you find a segmentation fault now, after this you can explain to yourself. And why usually people are asked in the Facebook, they tell me that they have segmentation fault. Usually I can really guess where the fault is, and they will find it out really this is their fault. I just hear, when I hear it, I can already know it because I know this part. Okay? So what is this part is about? This part is about 4 main topics. 4. Okay? Not concerning the kernel. No kernel is involved. Remember, segmentation fault is not about kernel. It's CPU tell you there is something wrong. It's CPU stuff. Okay, so these four guys, I will do it in reverse order. I will first explain to you what is code, and then go to go to global variable, go to malloc, and at the end we have stack. And after I finish these 4 topics, I will tell you how to generate segmentation faults. Okay, so first of all, addressing. This part I suddenly find it is useful since 3 years ago. 3 years ago, suddenly people tell me that, hey, I don't know what is the meaning of an address. I feel so shocked. Okay, what is an address? You don't need to know what an address before you code anything, right? Usually you believe in the system. The system, you declare variable, okay, or you declare constant. I don't know what kind of things. Once you declare something, you will have an address. And some people ask me, hey, what does that address mean? Okay? I can only give you some rough idea. What is the rough idea? The rough idea is the magnitude of the address. Now remember, this chapter, I highly relate all the things into Intel-based CPU. If you go to use an ARM CPU or using what kind of CPU? Or the CPU of your mobile phone, then the behavior will change. I will show you magnitude-wise comparison, and usually we will have a program running, and you will malloc. Okay, you will have a local variable, you will have a global variable, you have a code. And how can I access your code address? How can I access your code address? Do you know? Do you know how can I know the address of a code, of your code? No one knows? Huh? No, just by running this program. How can I know the approximate location? I don't know what exact location. Now I show you the program. I mean, now don't laugh at this program. This program is very, very, badly written. Okay? So I have this program. Can you find a line that I say it is reporting the code? Can you find a line? Which line? 1, 2, 3, 4. Printf. Which printf? The fourth printf, right? Look at fourth printf. And what is the fourth printf is doing? Yes. Then you understand why I say it's badly written. Do you know what it is? First of all, how many of you don't know what is %p? Okay, one don't know. Print address. Okay? If the variable that I say is an address, it will print out as an address. That's all. %p. Okay? And what is the parameter that I fit into printf? I give a name, this name, okay? Name is nothing, okay? The name is constant pointer, and what that constant pointer is storing is equal to a string. Hello. What is it? What is this? And I say that hello is the code and constant. Okay? Now it is because you didn't learn how to write assembly code. Okay? When you know how to write assembly code, you understand usually when I write assembly code in Intel CPU based Intel CPU layout, for memory storing code will be adjacently, okay, adjacently. They are put in side by side, constant and the code, they will put it side by side, and together put into one memory zone. The zone usually we give it a name called test segment. Usually called test segment. And that's why I usually say that, okay, when I print a constant out, okay, I will say that this is my memory address for my code. And also I will print out my global variable address. Malloc, I call one malloc. You know, when malloc returns, it gives me a pointer, and the pointer will point to the area for malloc. Right? So I malloc 4 bytes, and I receive it, and I just print out the address. What's next? Is something that you don't know what it is, maybe, in malloc pointer. Now this is a pointer. Pointer is just a variable. Now don't treat pointer as a special thing. It is just a variable, and variable size is 4 bytes. That's all. I mean for 32-bit CPU. Okay? 64-bit CPU will be wider. Okay? And I say that I want to retrieve its address in. So that means it's a local variable address. I show you the address of local variable. I show you address concerning malloc area. I show you address of a global variable, as well as show you the code. Give you one more. Give you one more. Do you know what I'm doing? Wow. Wow. Where's main? What's main? Main is a function pointer. It's a pointer. When I write it this way, it means inside the area, storing constant, storing code, I retrieve the location that the process storing my function called main. Okay? Compile, execute. Okay, so how to decode this address? The address, you can see this is from big address all the way down to small address. Right? The magnitude-wise is big to small. Okay? And look at the small part first. Can you see this? The code and the constant are very close together. They're very close together. really close together. Just differ by the what is meant to here. 16 times 16, okay, is something like that. Around 3 and 3. 3 goes together. And the global and the constant also very close together. Very close together, but already much wider, the gap is much wider than these two. And the global zone, global is kind of adjacent to the global zone, but already another order of magnitude are separated. How about malloc and local variable? Even wider. Wow, not just 1 minute. I don't know how to describe this scenario. Very, very big gap in between. Okay? So back to my PowerPoint. Oh, not this one. It's actually laid out in this way. The memory for Userspace program is laid out in this way. The small addresses in this area is not necessarily starting the code from 0. Usually it's not. Usually it's not starting from 0, some random address. And then you will have a bigger and bigger address laid out in this way. Okay? And usually it's 100% sure that it's always in this way. Okay? Except you use another CPU that I don't know. Okay? For Intel CPU, always in this way. So I need to explain to you, this is what I look at a process. Okay? And now it's already given some idea. What is the idea? The idea is, if I have an array, then let's say the array is in a global variable zone. I access it, but I go out of range. Go out of range. I keep on writing it, go beyond the bound of that array. Then actually, you will have a chance that you access the memory for malloc, because they are adjacent. Or you malloc a piece of memory from malloc, you go out of bound, keep on writing, keep on reading, then you may have a chance to touch the stack, because they are adjacent. They're really adjacent. Or do it in a reverse way, you do a decrement from a global variable zone, you can touch the code, because they stay together. Okay? And this is why sometimes you go out of bound, there's no problem. You just touch another people's house. Okay? You just you want to go back to your own house, okay, so happen there is another house there. Okay, so you go in there, no problem. That owner won't expel you, that's okay. Okay? This is part of the secret. This is not the entire secret. And for addressing, we start the smallest address with 0, and the biggest address with 0x 8f. 8f. Okay? So why is 8f? 1f means 4 bits for 1f. And we have 8f. 8 times 4 is 32 bits. So that means this is the biggest address that I can represent in a 32-bit CPU. 32 ones. Okay, there are 32 ones. And this 32 ones, okay, let's say every address representing 1 byte. Okay, every address is representing 1 byte. So what is the largest space that you can address? For example, I have a smallest address 0. So I address 0 to this number, and this number so happen you can deduce it and become 4g minus 1. G is 2 to the power 30. So that means the addressable area per process, the physical limit is 4g. No matter how many G of memory you have, no matter how. You say that, I'm super wealthy, okay? My computer has a 128 G. No problem, yeah, just pay it, okay? No problem, you can plug it in, but your process depends on your operating system. Your operating system is 32 bits, sorry. You are limited by this number. You cannot have a program calling malloc infinitely to get as many as possible because you're bounded. If it is 64 bit, Then it will become 2 to the power 64 minus 1. I don't know how large it is. Okay? Yeah, sometimes later on, okay, I will try. I will try using the common machine. Okay? Start a while one melon. Yeah, and try over the 64-bit CPU when my program will stop. Okay? So understand? And something that is also missed in this curriculum. The curriculum, how come people don't tell you about a machine code structure? Okay, because the machine code structure tells you some very important thing. Okay, so this is only for CES and CE. CE major you know it. Okay, CS major don't know. IE major you should know it, right? No. IE major, do you still have the Then you're right. It's only CE left, okay? And also minor know this. How come minor know it and major don't know? Okay, so this is an instruction. Why I show an instruction to you? Because every time when you have an instruction, let's say the instruction is addition, we need to add 2 numbers. And what is this 2? We call it operands. Usually we don't call it arguments. For machine codes or instructions, we call it operands. And usually these operands, when you are accessing a variable, we never say that, it means add A, B. No. It usually translates into memory address. Translate memory address become add some address in your local variable zone, another address maybe in your global variable zone. And this is the moment that you may generate an application fault because your operand, I don't know why you fit in the operand with the wrong address. But usually it's not the case, right? Usually you write variable A and B, and the compiler will do the translation for you, unless you use pointer. When you use pointer, then it is a chance that you override the translation that's done by the compiler, and you fit in address by yourself. And that's the moment that you may generate some application faults. Okay? So remember, these 2 eventually become addresses. And if you don't know what is address, I'll refer to this example. I guess this example should be okay, right? I don't need to explain. Huh? Oh no, your Java is taught by me. Then I know you don't know. Okay. Yeah, I teach Java, that this year we don't see it. Okay, so 2 years later, I don't need to explain this anymore. Okay. So that's, you use pointer. So what is pointer? Pointer is a piece of address. And I keep on explaining to you, a pointer is a 4-byte variable. I mean this. You create a local variable called PTR. Now remember, this is the first step. You create a local variable called PTR, and this so happens that you want to save an address. But for the compiler, I don't care. I allocate 4 byte space to you, and that 4 byte space is stored in here. Stored in the local variable address zone. It won't put it here because you write it as a local variable. Okay? And it so happened to store an address, so I write something look like an address, ABCDEF00. It so happened to look like an address. And when I try to access, want to dereference it, let's say I want to dereference it, before I can dereference it, I need to save an address, right? When I save an address, I will do something like this. And then save an address to here. When I dereference it, it means I pull out the address, look at the address, and follow this address, guide me to the location that you want to go. Okay? So let's say this is ABCDEF00. Maybe ABCDEF00 is here. Okay, so you guide me to here when I dereference this pointer. Okay? So I think I run out of time. Next, I will show you something horrible. Okay? Now, before we go to next, answer me this question. You go home, try to run this program first. Can you find any problem with this program? Huh? Can you find any problem? Is it okay to do it? Can I change hello to hell? Then you know hello, and the last O, I'll remove it, make it become a non-terminator, then hello become hell. Is it possible? Ooh. What do you think? Don't need to think it. Go home, compile the program. Tell me, can you compile it? Tell me, can you compile it? If you can compile it, can you run it successfully without segmentation faults? Okay? So, we will meet on a Monday. See you guys.